Now, in this board and sessions, to give a bit of a revision, we are showing more or less the equivalence of an NFA and a regular expression. So you can go from one to the other, and that's what we're in the process of proving. And the proof is a two-part if and only if, an IFF type proof. And we've just begun. So we're doing the if, the usual pure mathematical convention. You start with the if part first. So if you have two mathematical statements, P and Q, so typically an IFF, an if and only if type theorem statement would be of the form P if and only if Q, or P IFF Q. And if you do the if part first, that in other words P if Q, so that means P is true if Q is true. So in other words, if Q then P, okay? And that's what we're in the process of doing now, showing if Q then P. In other words, you start with the right hand side, Q, and derive P. So you deduce the left hand side. And that's what we're doing now. On the third session of this board, we'll do the other half, the only if. So we'll start with the left hand side, in other words P, and deduce Q. And in the process of doing that, introduce what's called a generalized NFA. And what is that? Well, jumping ahead a little, the only difference between a generalized NFA, in other words a GNFA, and an NFA, is that with a GNFA, instead of having symbols from an alphabet on your transition arrows, you have regular expressions. Okay? So it's generalized in that sense. Now those regular expressions could be just symbols in an alphabet, that's possible, but more general, hence the name. And that'll take us to the end of the board. Alright, so so we're doing the if part. Let's get back to the theorem. I'll read it out again, because it's getting quite involved in the sense many parts, and I can't put it all on just one board. Okay, so what we're talking about is theorem 1.54. Okay, and I'll just read it out. A language is regular, so call that P, right? If and only if some regular expression describes it. Okay. Now we're doing the if part first, and Sipser split the. He made the if part a lemma. He also made the only if part a lemma. So the if part's lemma 1.55, and the only if part, he will make that lemma 1.60. Now remember, he's using global ordering, so he's got various examples in between the two lemmas, and they have their own numbering. Okay, so so we're doing the if part, and to prove the if part, so here's the lemma statement. So a language is described by if a language is described by a regular expression, then it is regular. Okay. So we're starting with a regular expression, and we have to prove that it's regular. Now, how do you do that? How do you prove something is regular? Well, what does regular mean? What is a regular language? When it says it's referring to the language, of course. Maybe I should sort of, as a bit of revision, make the general remark. I think I've done it once or twice before, but it's sort of the basis. That is, this whole idea of equivalence between NFAs and regular expressions. Where does that come from? What's the motivation behind it? Well, if you have a language, whatever language it is, that language is described by an NFA. Sorry, a regular expression. It's described by a regular expression. But that language is, let's say that same language is recognized by a particular NFA, right? Same language. So that would make it seem intuitively obvious, I guess. Given we're talking about the same language, and it's described by a regular expression, and it's recognized by an NFA, then given it's the same language, you think there should be some sort of correspondence between the two things, the NFA and the regular expression, right? That seems intuitively obvious because they both revolve around the same language, and that's the point of this theorem. No, not the lemmas, not the if part and the only if part, but the whole theorem. That's theorem 1.54. Okay. Now, so the lemma, the if part, if a language is described by a regular expression, then it is regular. Okay, so we're starting with a regular expression. We've just got some regular expression, whatever it is, and then we have to show that regular expression is the language that it describes is a regular language. So how do you do that? And that's the proof, right? That's the if part of the proof. Well, what does it mean if a language to be regular? Well, that means that there's some machine, there's some automaton that recognizes it. Okay, and that's the clue. It's the strong clue to the proof. So if we can construct an NFA, because they're easier to deal with, less states. So let's, as the heart of the proof, the main proof idea, let's construct an NFA that recognizes that language. Okay. Now, how to do that? So that's the main idea. But how to do that? Well, a regular expression. Now remember, we talked about dividing up a regular expression into like 6 parts. You can define a regular expression in terms of really basic components that themselves are regular expressions, like a symbol of a language, of an alphabet, symbol of an alphabet, the empty string and the empty set. So they're really basics, and then you can combine those to form more complex, larger regular expressions by using the regular operators, union, concatenation, star. Okay? So if we can, for each of those 6 types of regular expression, if we can construct an NFA for each one and be able to combine them, we can create an NFA that recognizes that regular expression, whichever one it is. And if we can do that, then we have found an NFA, a machine, an automaton, that recognizes the language that the regular expression describes. Okay? Well, if we found a machine that recognizes the language, by definition, that means that that language is regular. And that's what we're trying to prove. Okay? So it boils down to, for each type, the 6 types of regular expression, we have to find a corresponding NFA, and then we can combine the NFAs, and we'll do some examples of doing this. You're given a regular expression, and then find the corresponding NFA, and we'll do that several times as examples. All right. So now we just started previous board, the end of the previous board, of showing how to construct an NFA for the 6 different types of regular expression. And so we just got into the first one, so we'll just continue on in this session. Right, so you can define, in the definition of a regular expression, you start with the most basic, the simplest types, and then build up to more and more complex regular expressions. So you can have as components, as parts of a more complex regular expression, as parts you can have simpler ones, and you can break those simpler ones down into even simpler ones until you get right down to the simplest regular expressions. Well, there are three. So 1, 2, 3. And the simplest either you can take an element of an alphabet, like a symbol of an alphabet, right? There's just little a here. That's just one symbol belonging to some alphabet. So that symbol, that is a regular expression. You'd find that to be a regular expression. Another very simple one is. Oh, by the way, my son-in-law. I have a very bright son-in-law, and he's following this course. I mean, he bought the textbook